Every single day, your heart moves 2,000 gallons of fluid through your body. Over a lifetime, it generates 2.5 gigajoules of energy. That is enough physical output to drive a heavy-duty truck to the moon and back. If you look at this scatter plot mapping heart rate against lifespan in the animal kingdom, you'll see a strict biological ceiling. Whether it's a hamster heart racing at 400 beats a minute or an elephant's heavy, slow pulse at 35, almost every mammal gets about 1 billion heartbeats before structural fatigue sets in and the organ fails. But humans deviate entirely from this trend line. Thanks to our specific physiology and modern medicine, a human heart can easily hit 4 billion beats over an 80-year lifespan. We are running a high-performance engine continuously, every second of every day, without it ever seizing up like a mechanical motor would. Yet, for all its endurance, the heart is still subjected to constant mechanical wear and tear.
To understand how we pull off this extreme biological marathon and how to keep the system from breaking down prematurely, we have to look under the hood at the heart's unique plumbing, its built-in electrical grid, and its highly specialized fuel system. The pumping capacity comes down to a highly asymmetrical floor plan. The right ventricle only needs a thin muscular wall because it pumps blood a very short distance to the lungs under low pressure. The left ventricle, however, is a massive slab of muscle designed to generate enough extreme pressure to force blood through 60,000 miles of vessels. The powerful left ventricle ejects blood into the aorta, functioning like a municipal water tower. The heart shoots fluid into this reservoir, creating the Windkessel effect. The elastic walls distend to absorb massive volume, then slowly recoil, maintaining a steady, continuous pressure. To make sure none of that high-pressure fluid moves backward, the system relies on 4 strict one-way valves. The ones separating the upper and lower chambers are anchored by chordae tendineae, essentially biological heartstrings. When the ventricles flex, these strings pull tight, keeping the valve doors from blowing backward under the intense pressure. By pairing this incredibly strong asymmetrical muscle with a flawless one-way valve system, the heart manages 2 completely separate pressure environments simultaneously without ripping itself apart. A muscle only flexes when it receives a signal. Unlike your biceps, which require a command from your brain, the heart runs on its own independent electrical grid. A cluster of cells in the upper right chamber, called the SA node, acts as a natural pacemaker, spontaneously generating the precise electrical spark that commands the heart muscle to contract. As that spark travels down, it hits a vital checkpoint called the AV node. This node deliberately holds that signal for roughly 150 milliseconds. That microscopic delay is essential. It gives the lower chambers just enough time to completely fill with blood before they squeeze. Perfect electrical timing is useless without the fuel to execute the contraction. The heart beats 100,000 times a day without fatiguing because its cells are packed with mitochondria, the structures that generate cellular energy. While skeletal muscle is only about 2% mitochondria, heart muscle volume is up to 35%. These mitochondria sit nanometers away from internal structures at specialized contact sites called MANs. When the electrical spark hits, calcium ions rush across these microscopic gaps. This directly tells the mitochondria to instantly ramp up ATP production at the exact millisecond the muscle needs it. Because of this dense, highly communicative energy grid, the heart never builds up the lactic acid that makes your legs sore after a run. It actively recycles the lactate produced by your other muscles, burning it as pure, premium fuel. If exit valves narrow, a condition called aortic stenosis, the left ventricle pushes against massive resistance. The pump fails in 2 ways. In systolic failure, walls turn flimsy and lose their squeeze. In diastolic failure, muscle grows so thick the chamber barely fills. The electrical grid is just as vulnerable as the plumbing. Chronic exposure to stress hormones keeps the pacemaker overstimulated and drives up vascular pressure, forcing the system into the red. Heart attacks routinely spike on Mondays. The psychological stress of the workweek triggers acute surges in blood pressure, overwhelming an already strained electrical system. Heart failure is rarely a sudden stop. It is a slow structural warping that happens when we force our biological engine to constantly operate against high resistance. The good news is that daily maintenance actively reverses this resistance. Laughter, for example, releases endorphins that relax the endothelium. This is the inner lining of your blood vessels. As the vessels expand, the physical resistance drops, giving your heart an immediate break. Managing those massive weekly stress spikes, especially on Mondays, keeps the electrical grid stable. It prevents the erratic firing of your internal pacemaker and keeps the rhythm smooth. Regular aerobic exercise feeds the mitochondria, forcing the heart to recycle systemic waste into energy and strengthening those microscopic calcium pathways so the muscle stays highly responsive. The heart isn't doing any of this work for itself. It generates all this pressure to supply the rest of your organs. Every day, the heart pumps your entire blood volume through your kidneys 20 to 25 times, just so it can be filtered and cleaned. It is the most resilient engine on Earth, designed to beat billions of times to keep every other system in your body alive. But safely reaching that evolutionary finish line relies entirely on the daily maintenance of its owner.